This is the video presentation for the solar tracking array that was designed and assembled by Joel Keys. The project was inspired by an ISU professor who was working on a similar problem for large format solar panels. I took that problem that he was working on, the project, and took it a couple of steps farther to enable it to react and track unpredictable heat sources. The applications for this project I projected onto cameras, night vision goggles, anything that any heat sensitive, light sensitive input device that operates at its highest potential with the greatest saturation to the input. The system is made up of an Arduino 2560 Mega microprocessor board, a Rio-Rand MG90S servo motor. That motor is for tilt of the solar panel. A NEMA 8 bipolar stepper motor, which is attached to the rotational arm of the solar panel. It is being driven by a StepStick A4988 stepper motor driver. The solar panel itself is an Adafruit 110mm by 140mm solar panel. The sensor array is made up of 4 Adafruit 10K thermistors, thermal heat sensors, and the code for the system was developed in the Arduino IDE. The 4 thermistors are set in an XY configuration in a box that is on the same plane as the solar panel. Initially, this box was left open, but it proved that the thermistors were influenced easily by atmospheric changes in the room wind. Even me moving would create temperature fluctuations in the thermistors. The serial monitor readout on the Arduino IDE is showing the temperature fluctuations without any stimulation. That is just the open thermistors in the room. I designed an enclosure for the thermistors, a 12mm by 12mm by 13mm cube with a 3x3mm window cut in the top of it. This is set on top of the thermistors and allows for protection from atmospheric or environmental changes. It is also theorized that by enclosing the thermistors with a viewing window in top will create a more accurate environment for the thermistors to read from. When the heat source or light source is 90 degrees, all 4 thermistors are being exposed equally and in theory will have the same temperature. But once the heat source starts to move, the opposing thermistors will have an opposite event happen. The thermistor in the direction of the heat source movement will now be in theoretical shadow, and the one opposite will have more surface area being exposed to the heat source. The code on the microprocessor will then make the stepper motor and or servo motor move to accommodate that motion because it has been coded that all 4 thermistors want to be equal. So they will seek the positioning where they will be set equal. The serial monitor readout is now indicating that all 4 thermistors are at equilibrium with the box in place, or the enclosure of the box in place. I did individual testing on the X and the Y axes. The servo motor is for the tilt, so that is the Y axis. The stepper motor is the rotation, which I set to the X axis. The stepper motor was more than responsive enough to the code and the thermistors, etc. However, when I put the whole device together, it proved that it was underpowered to be able to rotate the arm, the motor, the solar panel, and both of the wiring harnesses. Individually, those aren't very heavy, but when you put them together, they cause to be too much for the stepper motor. That in turn, I ended up blowing 4 of the capacitors for the power supply. I believe on that 4th one, it actually blew the driver motor chip. So I wasn't able to go any farther with rotational testing. I was able to move forward with testing. What I have done is I have the thermistors enclosed, and then I'm using a video production light as a heat source, and I will use it as stimulation just by turning it on. It'll create heat on the opposing thermistors. Alright, and I'm going to begin. As you see, it is reacting to the heat source, and it is following that heat source on the X or the Y axis. But then, as you saw, it took a moment for it to recognize that the heat source was on the other thermistor, and now it is continuing in the opposite direction. Now it recognizes that it has gone too far. The thermistors, they are insulated, and they seem to, I'm going to unplug this for the moment. The thermistors, they seem to absorb and retain heat, and that way they are not able to return to equilibrium with the others, or to recognize a change in direction of the heat source. The conclusion is that I need a stronger stepper motor to rotate the device, and some uninsulated, smaller mast thermistors that will be faster, or a different type of heat sensor that will respond quicker to change in stimulus.